Okay, today we're very fortunate to have Gabriel Brammer speaking to us about wide field slitless spectroscopy for JWST. Gabe's a member of the NIRS team, let's go ahead and just start your presentation.
Thanks, Christine. It's a pleasure to be here today in person and online, so thanks for people online that are tuning in. I'd like to tell you about some capabilities that we're going to have with the James Webb Space Telescope. I am particularly dealing with the wide field slitless spectroscopy mode. We know that James Webb is really going to be a spectroscopic machine in sort of the true sense with a multi-object spectrograph, but I think there's a lot of room for synergies and unique parameter space that's probed by this particular observing mode. And so I'm going to spend the first half of the presentation talking about some results that we've recently achieved from Hubble. This is a mode that's really seen its wide field use since the installation of the Wide Field Camera 3 in 2009. And I think really points the way with what we'll be able to do with wide field slitless spectroscopy with James Webb. So on the first slide here, just to orient people who aren't used to seeing these types of observations, I just got a feel this is a single WFC3 exposure in the Goods North field. This is one of these wide area deep extragalactic survey fields. But hidden in this field, you see you've got lots of spectra. A single exposure of a 1K detector is full of spectra, hundreds of objects. But in this field is a Redshift 11.1 galaxy and its spectrum. Anybody see it? No. Well, you can't see it from no matter where you're sitting, but it's hiding there. And the point is that you don't have to plan these observations for an individual target. You just, if the object is in the field of view, you have a spectrum of it, and I'll show you later in the talk, try to convince you that we actually have a real measurement of this object. Here's one that's a little bit easier, a completely different field, actually a different grism, the bluer grism with Hubble that covers 0.8 to 1 micron, but there's a redshift 6 point few quasar in this field. And this one you can actually pick off by eye if you're used to looking at these things. Okay, well there's this thing here that you see, the top one there, you can see the spectrum itself is just a little bit shorter than all the others. And that's just because the neutral hydrogen in the universe is eating into the blue edge of the spectrum in an alignment break. And so if you extract a spectrum of this is now a quasar, redshift 6.2. You see this beautiful alignment break. And if galaxy spectra looked like this with Hubble, we'd be in great shape. And in many cases, I think we will get spectra like this of distant galaxies, both with the slitless instruments with James Webb and also, of course, with instruments like NearSpec and higher resolution spectra. Okay, and so just one more little bit of review here. Here's a spectrum of the brightest object in the sky, the sun, a shell spectrum. That's sort of perhaps what people are used to looking at. You see, you don't have any spatial information really, but in this case, you've got very high spectral resolution where you can tease apart all these absorption lines and spectral features, emission lines if they were there. And here's another observation of the sun taken during an eclipse. And I forget which year and which eclipse, but if you put a dispersing element in front of your detector of the sun, in this case in the eclipse, you see the continuum spectra sort of offset to the right, but you also see emission line spectra, in this case of the chromosphere, and these are lines of Brammer lines of hydrogen and ionized iron and other lines. But what you can see here, and I'll show lots of examples of these of much more distant objects. What you get here is a little image of the sun in each of these emission lines. So you get at the far right, you get a little image of the sun in H alpha and these other emission lines. So this is slitless spectroscopy with the sun, and if you go 40 magnitudes fainter, you get things like this now with Hubble. And this is a gravitationally lensed object, and again, another one of these wide field survey areas. And so this particular system, you have a bright lens at about redshift 0.6 or so, the bright thing in the center there, a massive elliptical galaxy. And below it, you see this little arc here, which is the lensed image of a bright but distant background galaxy that's been stretched into this arc here. And there's actually multiple images across the arc. And if you disperse this image with now the Hubble grism again, you see again basically what we saw in the case of the sun, that you have little images of this object here, this galaxy, in the emission line. So there's a doublet here. This is the O3 doublet that's only marginally resolved. This is the 5007, 4959 doublet here. This is H beta next to it, and then H gamma and H delta, and even some of the higher order Brammer lines next to it. And so sort of the power here is that you get little images of galaxies in emission lines at the resolution of these space-based instruments, in this case Hubble. And you also see that you've covered the whole band. You're cutting off here just because this is at the edge of the image, but the WFIRST spectra go all the way up to 1.6 microns, so you have complete coverage from 1.1 to 1, in this case 1.1 to 1.6 microns. Of course, there's no atmospheric absorption bands or interstellar lines or OH lines, things like that. Okay. So here's a broad overview of things that we get from Hubble. So these slitless spectra are ideal for uniform coverage and spectra of large and what I call unbiased samples, basically just because you haven't made any pre-selection on things that you put slits on. And so an example I'll show is redshifts and measurements of 40,000 galaxies or more in these candles fields, these survey fields. I showed the one example. You get nice spatially resolved emission line diagnostics at HST or eventually JWST resolution, which gives you things like maps on star formation activity, spatially resolved maps on star formation activity, dust obscuration, metallicity, other things traced by emission lines. You also get low resolution continuum spectra. With Hubble, it's been mostly done with stacks of objects because the sensitivity is fairly low. The galaxies are faint. But for particularly bright galaxies, in some cases lens galaxies, you get nice absorption lines or continuum diagnostics of these galaxies. And then I'll emphasize that these benefits come at the cost of significant and formidable data analysis challenges, just because, again, in the first image that I showed, you saw you've got all these spectra, but in principle you have all these spectra sitting on top of each other, and you have to sort that out. And so the second half of the talk, I'll give an overview of the wide field slitless modes with James Webb. And just to mention here, I'm not going to talk at all about a lot of the exciting science that's been done with Hubble and that will be done with Webb on time series observations, measuring things like atmospheres of exoplanets and things like that. That's more single object slitless spectroscopy. And Jonathan Frayne is going to give a talk on June 6th on that, including the slitless capabilities for that science. Okay, so here's another example of sort of what this looks like in practice. This is a galaxy cluster field, MAX 1149, that was observed excuse me, by the GLASS survey. And so if observationally you take an image in a normal filter, in this case the H-band filter with WFIRST, and then when you switch the filter elements and get the dispersed image, it looks like this. And again, this now shows very clearly that particularly in the centers of these galaxy clusters where you've got lots of galaxies and lots of crowding, the spectra are all sitting on top of each other. And so what we do in practice is we have to model all these spectra where we know what the sort of general field looks like based on this image that we have. We know the calibration and the sensitivity of the grisms, and you can make a full two-dimensional model of the image that looks like this. And if I blink back and forth between them, you see it's a very high fidelity model of the entire field. And so then if you want to extract a single object like this one, a given spectrum can be very highly contaminated, but we can subtract that out. And if you take, in this case, we take these exposures at different orientations of the spacecraft, and that changes the relative contamination of the spectra of any given object. And if you subtract that out, you can basically see what's left here is there's a little emission line at the same wavelength in all of these different position angles, and when you add them together, you get a robust measurement and a detection of, in this case, an emission line. Okay, and so here we've done this in sort of an automated way for this wide field survey called 3D HST, and so this is just an overview plot just showing, I think, as many as 40,000 galaxies in the field where this modeling and extraction has all been done automatically. And now if I just plot the spectra, 1D spectra shifted into the rest frame and sort them as a function of redshift, you see the different line species as they go through the grism bandpass there. So H alpha up to redshift 1.5 or so, H beta no 3 up to redshift 2.3. And again, these are all the galaxies in this field, reliable redshift measurements, and also these other diagnostics. Okay, and so the reason why you want to do this is we've got now highly complete spectroscopic coverage of these things, and what we typically do with these types of observations is treat them as an overall galaxy survey. What are the properties of the galaxy population in these survey fields? And the best, I think the most robust way to do that is when you've got uniform high-quality observations of every object in the field. And you can do things like, again, take these spectra, shift them to the rest frame, and now sort them by stellar mass, and you can see things like the H-alpha emission equivalent width, how that varies as a function of stellar mass. You've got very high equivalent width lines at low stellar masses and basically absorption line spectra at the very highest masses. If you sort by the inferred dust obscuration of these galaxies from their broadband SEDs, you see, again, similar trends that you expect, but it's nice that they fall naturally out of the spectra, that if you look at the H-beta and H-alpha lines in particular, you can basically read the Ballmer decrement off of these spectra here. Okay? And so one reason that this has been powerful with Hubble is that it allows you for efficient pre-selection of targets that you want to go follow up with very deep observations, say from the ground, or in the future perhaps with JWST NearSpec. And this is just an example from a recent paper from Reinhard Genzel et al., where they find these, with very deep ground-based IFU spectra, evidence that the rotation curves of these galaxies are falling over at large radii. And again, these galaxies were selected as from redshifts and also the H-alpha line fluxes from the 3D-HST survey. So it's a very efficient way of finding targets for detailed follow-up. Okay, I'm not going to say very much more about stars. I mentioned it in the abstract, so I wanted to include a slide that you actually get the best wide-field slitless sensitivity for point sources just because you're sort of spreading the spectrum out over fewer pixels that are sky-limited. And so it's actually very efficient for getting very high signal-to-noise spectra of stars. And so here's an example of some features. This was a survey of brown dwarfs where each of these targets is in an individual pointing. But you see these very strong absorption features, the water feature here at 1.4 microns, and of course that's also what's being observed in some of these exoplanet atmospheres. But these are very short, less than an orbit exposures on these brown dwarfs. And again, if you go back to 3D-HST and do this game of of plotting and sorting the spectra, so here I've just plotted 1D spectra of stars sorted by their I minus J colors, and you can just see these spectral features as they come in the redder spectral type. So in M stars, you start to have this 1.4 micron absorption feature. So you can measure fairly reliable spectral types, at least of redder stars, in a sort of a blank survey sense with these observations as well. Okay. And so I started out by mentioning, I think one of the biggest strengths of these observations is the fact that you get these high-quality emission line maps of galaxies at modest redshifts. And so that tells you about star formation rates as traced by perhaps H-alpha, perhaps the star formation history. If you look at where the H-alpha, or the ongoing stars, or the newly formed stars are compared to the continuum, which is where the older stars are, that gives you some idea of a spatially resolved star formation history. You can measure spatially resolved dust extinction, perhaps metallicity gradients, and also perhaps local environment, because again, with no pre-selection on objects, you're quite sensitive to nearby neighbors and also the local environment of these galaxies. Okay, so here's an example of another dramatically lensed galaxy at redshift 1.7. So this arc here is behind a foreground cluster at redshift 0.4 or so. And so there was a Slitless program that was published by Kate Whitaker in 2014, where you can see that you can make a very nice, effectively narrowband image of this galaxy in the O3 line across the whole length of this arc, again with HST resolution. So this is the kind of thing that you can do with the Grizzly. And so here's an early paper from Stein-Weitz when we first started the 3D-HST program, making both stellar mass maps of galaxies based on their continuum images, the broadband continuum, but then also comparing that to H-alpha direct maps measured directly from the Slitless observations. And that tells you, again, where the ongoing star formation is in these disk galaxies at redshifts 1 and higher. Okay. And then for larger samples, Erika Nelson in her PhD thesis looked at these H-alpha maps for large stacks of galaxies now in 3D-HST to look at the average properties as a function of stellar mass and other galaxy parameters. And what Erika finds is that these H-alpha profiles are smooth. I mean, that's part of by construction because of the fact that she's stacking many galaxies together here. But that galaxies from 10 to the 9 up to 10 to 11 solar masses have these star formation profiles, or H-alpha profiles, that are roughly exponential in all of these stellar mass bins. And when she compares that to the profiles of the continuum, she finds that the H-alpha is somewhat more extended than the continuum, and that's some evidence that for inside-out growth of these galaxies, basically the stars that are already there, that were formed earlier, are more, have a more compact morphology, so they formed earlier. And so these are the kind of things that you can do with the Slitless spectroscopy. And then for continuum spectra, this is a stack from spectrum from Kate Whitaker, looking at stacks of massive galaxies, and where you don't have to look at the details here, but all of these broad absorption features are truly absorption features of magnesium and the calcium G band and other absorption features. And one thing Kate also finds is that there's some evidence here for an excess of O3 emission. Even in these very massive galaxies, the star formation rates are essentially zero, so perhaps there's some evidence that for some low-level AGN in the very centers of these massive galaxies, and that comes again from the spectra. And then for particularly bright cases, and again, usually helped by gravitational lensing, you can do things like extract spectra along the major axis of this particular galaxy here, and look for gradients in these absorption line spectra and stellar population properties. And here's one where, in this particular example, the top here is the central kiloparsec of this object, this lensed galaxy, and the bottom here is the outskirts, greater than 1 kiloparsec. And though there's not quite enough signal to noise in this particular example to tell much about the absorption line spectra, you do again see evidence for there being line emission, O3 line emission in the central regions of this galaxy. And again, with this GLASS survey, Tucker Jones and Chen Wang have written nice papers looking at, again, these mission line diagnostic maps, but using them to measure metallicities and metallicity gradients in particularly bright lensed examples of these things. And so what Tucker finds is a relatively shallow metallicity gradient, which is consistent with some interaction between these things that, or perhaps enhanced feedback that makes efficient outflows and mixes the material in these galaxies. Okay. So the last little bit of results from Hubble here is really using Hubble to push out to the very highest redshifts. And so this is getting back to this Redshift 11 galaxy that I showed at the beginning of the talk. And so the top panel here shows the full 2D spectrum around this Redshift 10 or 11 candidate that was selected from photometric observations. And now on the bottom here is the full model that we've made of all the contaminants. And again, this model knows about the brightnesses and the spectral shapes and everything of all the contaminants. And so if you subtract that off, you're basically left more or less with Poisson statistics of the background here. And this excess here with a little break at 1.5 microns, which is fully consistent with this model of a Redshift 11.1 Lyman break for this galaxy. And so here's another view of it now in the 1D spectra, that you see basically essentially no flux below 1.47 microns or so, and then this excess that's detected at about 4 sigma. And again, that corroborates evidence from the photometry. The photometry already told us that the redshift was almost certainly greater than 10, and then this is verified from the spectra. And so there's recent observations that suggest that maybe it's harder and harder to see Lyman alpha at these very high redshifts. That's the emission line feature that's typically used to measure these very high redshift emission lines. But perhaps because as you get into the reionization era, the universe is more and more neutral. It's harder for the Lyman alpha to get out. And so continuum breaks like this might be really the only, if not best, way of measuring redshifts, these very high redshifts. But we have seen some preliminary results at slightly lower redshifts, at least of detecting Lyman alpha with these slitless observations from the GLASS survey in these particular cases by Casper Schmidt in recent years. Okay. So I'll move on now to talk about capabilities. Basically, the data and the properties of the observations will look very much like everything I've shown before. But what JWST is going to provide great improvements over Hubble, particularly in sensitivity. It's obviously a much bigger mirror, and also image quality at factors of 2 or more better than Hubble. And also, I think, interestingly, increasing the bandpass, particularly for slitless spectroscopy. So Hubble only gets up to about 1.7 microns. in the H-band, but James Webb will have slitless capabilities out to 2 microns with NearSpec and out to, all the way out to 5 microns with the NIR Cam instrument. So a complete coverage there. So here's the field of view, or the focal plane of JWST. And so the instruments with wide field slitless capabilities for James Webb are NearSpec here. This is sort of more or less a dedicated wide field slitless instrument. And also NIR Cam that I'll mention. And I've got MIRI in parentheses here, and I'll explain that in a minute. There is a mode for wide field slitless spectroscopy with MIRI, though it's not currently planned as a science mode, at least for the early cycles. Okay. And so with this figure, I'm just zooming in on the footprints of NearSpec and NearSpec to try to highlight that I think, you know, though the NearSpec has all the same type of contamination and challenges that I've mentioned for Hubble, and whereas NearSpec, you're going to get, you know, you can put fixed slits on objects that you're interested in and get, you know, significantly higher spectra resolution spectra. It's very hard to reproduce the source densities that you can get with NearSpec over this 2 arc-minute field of view, because again, you know, if you go deep, you can get hundreds or even thousands of galaxies in this 2 arc-minute field, and that would require perhaps many pointings with NearSpec just because of slit collisions and you know, planning these multi-object observations. Okay, and so here's a view of the nearest filter wheel. So nearest, to remind you, saw on the previous slide, is just one H2RG detector with the 2 arc-minute field of view, 0.06 arc-seconds pixels. That's half the size of Hubble with C3. And so nearest has 2 wheels, a pupil wheel and a filter wheel, and so these 2 elements in this case for nearest, it's actually the filter wheel. You've got the GR150C and 150R grisms, so there's 2 elements, and I'll mention that again in a second. And in practice and observations, you then cross these grisms with one of these elements in the pupil wheel, which are the wideband filters that are basically designed to match the NIR Cam short wavelength wide filters. So going from 0.9 microns up to 2 microns, or the K-band. Okay, and so this already provides an interesting capability that's not available with Hubble with these 2 grism elements. And so in a single visit, if you take up exposures in one grism and then the other, the 2 grisms disperse the spectra in orthogonal directions and offset by 90 degrees. And so in a single visit, you can basically get 2 separate slices of this of contamination that I had mentioned earlier. And of course, JWST, the visibilities for a given target are harder to schedule and arrange than they are for Hubble necessarily. And so it's kind of critically important that in a single visit, you can get these 2 orientations to help break some of these degeneracies in the modeling and remove the effects of contamination. And so that there are templates that allow you to take these exposures in a single visit with NearSpec. In this case, these are both crossed with a single F115W filter. Okay, and again, to cover the whole bandpass from 0.9 out to 2 microns, it is a little bit more expensive with NearSpec because it does require separate exposures crossed with these the wideband filters. And I don't think it's allowed or foreseen to be allowed in the science observations to take observations with no filter, and you probably wouldn't want to, one, because all the orders would overlap and the background gets extremely high. Crossing them with these narrower filters actually helps the sensitivity observation just because it cuts down on the overall background. These are typically background limited observations. Okay, and so here's a view of what these spectral orders look like in the different blocking filters for NearSpec. So the bluest filter, you see the higher orders across the detector. The spectrum moves across here. This is a compact 0th order, which, you know, it can complicate analysis because that's what emission lines can look like for galaxies. But again, because of the way these things are calibrated, we know for a Bright's target where these 0th orders will lie in the detector, and so those are modeled as well as the first order spectra. Yeah, so there's the different filters there for NearSpec. And here's the sensitivities. So in about 10,000 seconds, you get to line sensitivities of significantly less than 10 to the minus 18 ergs per second per centimeter squared. That's factors of, you know, few better than even extremely deep Hubble observations that have been taken so far. And then here's just a quick overview of planning a NearSpec visit in APT. So you first, this is all enabled in the latest versions of APT. You can plan this yourself. So first you select a dither pattern. There's these predefined dither patterns for NIR, so you can look up what they are. They're typically fairly small, of order less than an arcsecond dither offsets. Again, there's no chip gaps to dither over with NIRS. You select the GRISM, which can either be one or both of these two orthogonal GRISMs, and then you select a blocking filter, and then a detector readout mode. And so NIRS only has two readout modes as opposed to NIR Cam, which has many. So there's the NIS rapid, which for a full frame requires 11 seconds, and for the NIS readout gives you about 43 seconds per group. And so the visit layout is that, once you specify this, you have a lot less flexibility than is currently with Hubble, where you can basically plan your orbits however you want. And so the nearest templates are such that it first takes an exposure in the direct image without the GRISM. Then it rotates in the GRISM element and then takes the four dithered exposures with the GRISM in, and then at the last position takes the GRISM out and takes one more direct image. And so in this case, with 4 dithers, you've got 4 GRISM exposures and two dithered direct images. And so that's all hard-coded in the templates, but you can select more or fewer dither positions with the GRISM exposures. Okay, and now moving on to the NIR Cam capabilities. So in the long wavelength channel, there are 2 of these orthogonal GRISMs, very much like I've shown earlier for NIRS. So there's a row and a column GRISM for NIR Cam, and again, just like NIRS, you then cross the GRISMs with an element in the filter wheel here for NIR Cam, which covers, again, this is just the long wavelength channel, so it covers 2.5 to 5 microns or so. And with with NIR Cam, you do have 2 detectors, 2 H2RG detectors that are basically twice the field of view of NIRS. And it's worth pointing out here, the dispersion of these GRISMs is actually quite high. It's an R of about 1500. And that comes from the fact that these GRISMs weren't originally installed for this application that I've been talking about, for wide-field slitless observations of stars and galaxies and things. I think they were originally planned for the wavefront sensing system with NIR Cam, but it was quickly realized that they had utility for these types of science observations that I've mentioned. So it does, make some things a little bit more complicated than what I've shown earlier. For one thing, just the spectra take up a lot more detector real estate because you've got this very high dispersion. So in the case of the broadest filter here, 322W2, which covers most of the long wavelength bandpass, the spectra you see cover the whole, basically the whole field of view of the NIR Cam detector. And even with the medium band filters, they take up about 20% of the field of view. And there are cases that you can imagine, this whole line map thing that I've mentioned at the beginning of the talk sort of works in that the dispersion of the GRISM is low enough that you're not actually spectrally resolving basically anything. But in the case of the NIR Cam GRISMs, where the resolution is quite high, it could potentially make your, these dispersed spectra of objects that are resolved spectrally, slightly complicated to a model and fit, because you then have to actually account for the fact that you might have velocity gradients across the galaxy. But, that resolution is about 200 kilometers per second. Most galaxies at the redshifts this will be sensitive to, that might not be an issue. Okay. And I think, there's actually a lot of capabilities for the NIR Cam GRISM, and in particular, one of the recent observations of very high redshift galaxies greater than 6 or so is this prevalence of very high equivalent width emission lines that are basically inferred from our current observations, which is just Spitzer photometry at these wavelengths. And so people have seen these large excesses in this case at redshift, I think, 6.8 or so. You have this large excess in the Spitzer 3.5 micron band, which, all reasonable analysis of the spectral energy distribution of these galaxies suggests that this is an O3 line with equivalent widths of more than 1,000 angstroms in the rest frame. So very strong lines, and there's some reason to expect that astrophysically this to be the case, just because these at very low metallicities and the ionization properties of these galaxies will also conspire perhaps to make these very strong lines. But that's good news, at least for the NIR Cam GRISM. that these lines will just pop out, that the high resolution, spectral resolution, you don't care so much about the continuum sensitivity, but the lines just pop right out, and the spectral resolution is high enough that you very easily resolve the O3 doublet. And so this is a quick simulation of taking this galaxy from this Smith et al. Paper and shifting it to Redshift 7.7, just an hour observation with the NIR Cam Grizzly in just one of the medium width blocking filters. You get very robust detections of this line doublet. So potentially a redshift machine for sort of blind searches of very high redshift galaxies. And so I mentioned this before, that MIRI has a wide field slitless capability, and that's just because if you put a target on the low resolution slit with MIRI, you basically still let light through the rest of the detector, and so you get little dispersed spectra of anything else that happens to be in the field of view here. But again, at least for cycle 1, that's, as far as I understand, that's not currently planned as a science mode, though it is there in the telescope. So an important, I think, thing to mention with the slitless is the capabilities of observing in parallel with coordinated parallels. And so this is now enabled for ERS programs in cycle 1 and also implemented now in APT. And so the available modes for at least wide field slitless for parallels is nearest wide field slitless in cohort with NIR Cam or MIRI imaging. Currently, it's not allowed to take NIR Cam wide field slitless spectroscopy and nearest wide field slitless. That might be available in future cycles. And then just a comment here that there's less flexibility than with Hubble for coordinating observations such that you flip the focal plane such that you can observe the same field with the two instruments, like has been done with, in this case, the frontier fields with Hubble, just to keep that in mind. But still, the coordinated parallels is an available mode. And so I also want to mention that in addition to the specific JWST, the analysis pipelines, that are taking the raw images from the telescope and producing science products, we at the Institute are developing additional planning analysis tools to help people prepare for observations and also analyze them. The first is, I wanted to mention this NIR Cam Contamination Simulator. So I showed earlier in the case of GNZ11 how hard, even in the case of a blank field, how hard it was to sort of pick an orientation where there's relatively little contamination of that single target galaxy. And so this tool by WFIRST allows you to specify a given position and an image, and it predicts for you what the contamination of your desired object will be as a function of position angle of the Grizzly. And so it allows you to, in this case, dark is good. And so, in very many position angles here, these bright bands mean that your spectrum would be very highly contaminated, though there are little windows here at particular position angles where you could observe and get a relatively clean spectrum of a specific target, I should say. And then there's another software tool that I've been developing called Grizzly, and this is primarily I've been developing this for the HST analysis, but again, the layout and everything of the detectors and the dispersion is such that it works, that you can make it work for these future instruments like James Webb and also WFIRST, and then you can actually download some of the simulated data that I'll show at the end here. We recently did an effort to basically do an end-to-end full simulation of some nearest wide field observations. So you can download those. These are FITS files that are basically going to have the structure of the flight nearest files. And so here's just a quick simulation of what one of these extragalactic fields might look like. And I think it's immediately interesting to notice here that the spectra with these blocking filters take up significantly less detector real estate than they do for Hubble. And so the contamination at a given depth is significantly less for nearest than it was even with Hubble. And again, with Hubble, I've suggested that we can at least model a lot of that out. But I think with nearest, that's going to be somewhat easier. Just because the spectra are smaller as measured in arc seconds on the detector, though we will go deeper, and so these things kind of play against each other. And so if you then simulate this field with the other GRISM, the R GRISM, you see that the field rotates by 90 degrees, and the relative contamination of, say, a given object is completely different. this object is sort of contaminated with this thing next to it, where now they're completely separate in the second orientation. So you can plan this. If you have an image of a field, you can make these types of simulations, and then simulate them with the other blocking filters. And so just a quick mention of the NearSpec GTO survey that's being planned. NearSpec is built by René Doyon in Canada in the CSA. And so the Canadian team is planning a large extragalactic survey called Canucks of 200 hours. And so this is something going to be similar to the GLASS survey that I mentioned earlier, but now with NearSpec, something like 6 hours per filter per target. And that'll give you these beautiful emission line maps now even in the K-band, so H alpha to redshift 2 or so. And in the same observations, the spectrum of GNZ11 now will look something like, more like that quasar that I showed in the first panel. So sort of unambiguous redshift determinations of Lyman breaks at very high redshift. And then I just wanted to mention in the very end here that it's worth thinking even beyond JWST and perhaps even overlapping with JWST, the launch of the WFIRST mission. And so WFIRST, the capabilities are very much similar to all these slitless observations that I've shown earlier. That's really one of the fundamental tool behind this large redshift survey for cosmology. But this WFIRST is going to be, the WFIRST instrument is, completely different parameter space than James Webb. It's going to have a very large field of view, 0.28 square degrees, which is going to cover a total of 2,400 square degrees now. I've been talking about square arc minutes, individual, of order of unity square arc minute observations for Hubble and James Webb. This is going to be, thousands of times larger, with a telescope about the size of Hubble, and a resolution sort of intermediate between the Hubble grisms and the NIR Cam grism. So it's about 4 times out of G141. And so here's just a little cartoon of the field of view of WFIRST overlaid on these large WFC3IR surveys. And so in a single pointing, you cover this area very quickly. And so I won't dwell too long here, but just to show these plots here for all the different missions are showing emission line species of H alpha, H beta and O3 and O2, and where you're sensitive to those in the different grisms and blocking filters for the instruments. So just to remind you, nearest here, we're sensitive to H alpha now out to redshift 2 or so, O3 out to redshift 5. And with the NIR Cam grism, you can extend these observations like the simulations I showed earlier, O3 all the way out to redshift 7 and 8 and into the reionization epoch, again, where it might be challenging to actually measure Lyman alpha for these galaxies. The O3 is probably just going to be popping out there. And then further along the line with WFIRST. So in summary, I think HST slitless grism surveys like 3D HST and GLASS and many others have shown a lot of promise and a lot of exciting results for, at least in what I've been showing for galaxy evolution science. They provide highly complete spectroscopy, spectroscopic samples for these fields. But it comes at a cost that you have to, it requires different analysis techniques than sort of standard imaging or standard spectroscopy for that matter, but with benefits of continuum depth, completeness, and also the abilities with these spatially resolved lines that I've mentioned. And we've learned a lot from these recent observations from Hubble, and that's sort of informing, I think, what we plan to do and how we'll analyze JWST observations. And I think I've tried to, highlight some of these unique capabilities and this unique parameter space that'll be, that you can probe with wide field slitless spectroscopy with James Webb, sort of intermediate between classical imaging and now the multi-object spectroscopic capabilities. So, thank you.
Gabriel, could you go back to the Canucks slide just really quickly? I just wanted to take this opportunity to advertise that from May 15th to 18th, we're going to have a proposal planning workshop here at Space Telescope. And the objective is to teach the user community how to use the proposal planning tools, in particular like the ETC, the APT, the target visibility tools. And the way the teaching will be done is by using specific GTO programs, so specific science use cases. So one of the, so the NearSpec team has very generously offered to share detailed information about the CNOOCS program. So Chris Willett will come to Space Telescope and give a 30-minute strategy, high-level strategy talk about how they have chosen to implement using wide-field slitless spectroscopy with NIRS for their GTO program studying these galaxy clusters and actually the kinds of complementary observations that you need to obtain to get the most out of your NIRS observations. So this includes, like, for example, higher angular resolution, better sampled NIR Cam imaging, and then also complementary photometry at longer wavelengths using NIR Cam as well, incorporating these coordinated parallel observations that Gabriel has spoken about. And then there will be, in concert with that, specific hands-on teaching sessions for the EPT, the ETC and the APT and the target visibility tools, where essentially Chris is passing us the exposure time calculator workbooks for their program and their final sort of, it's kind of a work in progress right now in that the final version of the APT files has not been submitted, but the GTO has been working on them. And so through these hands-on sessions, there'll be an instructor, for example, Swara will stand at the front of the class for the ETC and step people through, starting with an empty workbook, how to make the exposure time calculations for this particular program. And then the same thing will be done for APT, trying to understand in more detail how you use the target visibility tools to place constraints on your observations if that's needed, and also trying to understand other issues like overheads and how much time your programs take. So with that, I just wanted to point that out because Gabriel explicitly mentioned CNOOCS, and it's a really wonderful opportunity to learn more about that program if you're interested in that and using that as an example to learn. So aside from that, are there any questions here in the building at Space Telescope? I'm going to run around with the microphone so everybody online can hear you too.
Gabe, a few slides ago you showed a comparison with of the spectra on the real estate with NIRS and HST. Can you just remind me what the spectral resolution are? Is it smaller on NIRS because the resolution is lower?
The resolution is similar. They're both about R150, but the pixels are half the size for NIRS, and so in arc seconds the spectra are smaller.
Yeah, I see. Thank you.
Okay, I saw David had a question.
So it's actually extremely helpful. There's two different dispersion directions, effectively getting you two different roll angles. But for a typical extragalactic deep field, just for sense of example, will those two different orientations be sufficient to break the degeneracies for the majority of objects or some percentage of objects? And what amount of time will you still want to get some intermediate angles for typical fields?
Yeah, that's a very good question, and frankly, one I still don't have a great answer for how you optimize that. It depends on so many parameters, like, the contamination for relative contamination of faint objects is obviously typically much higher than it is for bright objects because a faint object is more likely to be contaminated, by a bright object. And so I don't have a good answer other than that, we don't have a sort of a classical confusion limit like you do with imaging. In a lot of cases, we have demonstrated and found that with the full detailed modeling of these fields, you can reproduce faint emission lines and things. But with 3HST, I think the numbers that we got, even in a single orientation, are something like 90% of usable objects had usable spectra. And so if you kind of, we don't have a good answer for how those statistics work out. But even 2 really helps a lot, and we fully explored how many, at a given depth and a given source density, how many types of orientations you need to really be guaranteed to have clean spectra.
Okay, thanks.
Are there any other questions here in the room? Okay, if not, let me just check online to see if there's any there. Okay, if anybody has any questions online, you can go ahead and unmute yourself and ask your question on WebEx. Oh, I see Crystal Martin has a question. Go ahead.
Can you hear me?
Yes.
Can you say a little bit, Gabe, about the relative strength of NIRS and NIR Cam for slitless spectroscopy?
I mean, they are complementary, and particularly in the fact that the wavelength coverage is disjoint between the two, so they don't directly compete at a given redshift. For continuum, I think the nearest sensitivity is significantly higher just because the spectral resolution is so much lower. For the wide field slitless, you're almost always background limited, and the continuum spectroscopy becomes hard as you disperse the spectrum over more and more background pixels. So my impression anyway is that, at least for continuum breaks and continuum features, NIR, just because it's so much lower spectral resolution, is more competitive. But really, I think they're just, can be seen as complementary. And I feel like the emission line sensitivity is basically similar. It's whatever the detectors have more or less the same sensitivity.
Are there any other questions on that one? Okay, I don't see any hands or anyone unmuting. So if not, let's go ahead and thank Gabe again. And then I guess our next lecture is going to be in 2 weeks. All right. Thank you.